Welcome, weary wanderer of the cosmos. As you settle in for a bit of rest and contemplation, I invite you to ponder one of the great enigmas of our universe, the mystery of dark matter. Before we embark on our journey through this perplexing puzzle, I'd love to know where in the world you're joining us from and what time of day it is for you. Please do share in the comments below, and if you find yourself enjoying these gentle explorations of science and history, be sure to subscribe so you can drift off to sleep with more soothing stories. Now, let us begin our tale, not with a bang, but with a whisper, a hushed hint of something strange stirring in the depths of space. For you see, when astronomers gazed up at the night sky and meticulously measured the intricate motions of stars and galaxies, they noticed something peculiar. The cosmos, it seemed, was dancing to a tune that didn't quite match the melody they expected. Imagine, if you will, the universe as a grand cosmic ballet, with galaxies pirouetting and stars swirling in perfect synchronicity. But as scientists studied this celestial choreography more closely, they realized that some of the dancers seemed to be moving too quickly, defying the gravitational pull of their visible partners. It was as if an unseen force was guiding their steps, an invisible hand gently nudging them along. This puzzling phenomenon first caught the attention of a brilliant astronomer named Fritz Zwicky in the 1930s. Zwicky was a man of intense curiosity and meticulous observation, spending countless nights peering through the telescope at the Palomar Observatory in California. As he studied clusters of galaxies, he noticed that the individual galaxies were moving much faster than could be explained by the gravitational pull of their visible neighbours alone. Zwicky's calculations suggested that there must be some sort of hidden mass within these clusters, providing the extra gravitational glue needed to hold them together. He called this mysterious substance dunkle materie, dark matter. At the time, his ideas were met with skepticism, but little did he know that he had stumbled upon a cosmic conundrum that would captivate scientists for decades to come. As the years passed, other astronomers began to uncover similar anomalies in the motions of galaxies and stars. In the 1970s, a brilliant young scientist named Vera Rubin took up the mantle of investigating these celestial oddities. Rubin was a trailblazer in the field of astronomy, defying gender barriers and forging a path for future generations of women in science. With her keen eye and innovative techniques, Rubin meticulously studied the rotation of individual galaxies, expecting to find that stars near the edges would orbit more slowly than those closer to the galactic centre. But to her surprise, she discovered that stars on the outskirts were moving just as quickly as those near the core, a finding that defied the laws of gravity as we understood them. Rubin's groundbreaking work provided even more compelling evidence for the existence of dark matter. She showed that galaxies were spinning so rapidly that they should have torn themselves apart if only the visible matter was holding them together. There had to be something else, some unseen gravitational glue, keeping these cosmic structures intact. As more and more evidence for dark matter accumulated, scientists began to envision it not just as a simple explanation for strange galactic motions, but as a fundamental component of the cosmos itself. They realized that this invisible substance wasn't just hiding within galaxies and clusters, but was actually woven throughout the very fabric of the universe. In the 1980s, two astronomers named Margaret Gehrler and John Huchra embarked on an ambitious project to map the large-scale structure of the cosmos. Using the powerful telescopes at the Harvard-Smithsonian Center for Astrophysics, they painstakingly measured the distances to thousands of galaxies, piecing together a three-dimensional map of the nearby universe. What they revealed was a cosmic web of breathtaking beauty and complexity. Galaxies weren't scattered randomly through space, but instead seemed to be strung along vast filaments, like shimmering beads on an invisible necklace. Between these filaments lay enormous voids, yawning expanses of seemingly empty space. As scientists studied this intricate cosmic web, they realized that its very existence hinted at the hidden presence of dark matter. Computer simulations showed that in the early universe, shortly after the Big Bang, tiny fluctuations in density could have been magnified by the gravitational influence of dark matter, growing over billions of years into the majestic structures we see today. Without dark matter, the cosmos would be a very different place. Galaxies would be smaller and more diffuse, stars would form at a much slower rate, and the grand architecture of the universe as we know it simply wouldn't exist. dark matter, it seemed, was the invisible scaffolding upon which the visible cosmos was built. But for all its apparent influence, dark matter remains elusive. Scientists have long sought to unravel its secrets, to understand what it's made of and how it interacts with the familiar matter that makes up stars, planets, and people. Over the years, numerous theories have been proposed, each attempting to shed light on the nature of this mysterious substance. Some scientists suspect that dark matter is made up of exotic particles that have so far eluded detection. These particles, known by names like axions, sterile neutrinos, and weakly interacting massive particles or WIMPs, are thought to interact only very feebly with normal matter, making them incredibly difficult to spot. In pursuit of these elusive particles, researchers have built incredibly sensitive detectors, often nestled deep underground to shield them from the constant bombardment of cosmic rays. Experiments like Xenon, ELEX, and Pandax use massive tanks of liquefied xenon, waiting patiently for the telltale sign of a dark matter particle colliding with an atom. Other detectors, like the Supercryogenic Dark Matter Search (SuperCDMS) experiment, use crystals of germanium and silicon cooled to just a fraction of a degree above absolute zero. At these incredibly low temperatures, the atoms in the crystals are nearly motionless, making it easier to spot the tiny vibrations that could be caused by a passing dark matter particle. Despite decades of searching, however, scientists have yet to directly detect a single dark matter particle. This persistent elusiveness has led some researchers to propose alternative explanations for the strange behaviours of galaxies and clusters. One such idea is known as modified Newtonian dynamics, or MOND. This theory suggests that instead of invoking dark matter, we might need to modify our understanding of gravity itself. According to MOND, the force of gravity might behave differently on the vast scales of galaxies and clusters than it does here on Earth. While MOND has had some success in explaining certain astronomical observations, most scientists still favour dark matter as the most compelling explanation for the cosmos we see. The evidence for dark matter's existence is simply too strong to ignore, even if its precise nature remains a mystery. And so the search continues. With each passing year, new experiments come online, each more sensitive than the last, each hoping to be the one that finally unmasks dark matter. It's a quest that has captured the imaginations of scientists around the world, a grand cosmic detective story playing out on the grandest of scales. As we lie here in the darkness gazing up at the stars, it's hard not to feel a sense of wonder at the mysteries that surround us. We are but tiny specks in a vast, inscrutable universe, our knowledge dwarfed by the enormity of what we have yet to learn. But in that humbling realization lies a profound beauty. For as we probe the depths of the cosmos, as we seek to unravel the secrets of dark matter and other enigmas, we are not just expanding the boundaries of our understanding, we are reaching out to touch the very fabric of creation itself. So let us drift off to sleep, our minds filled with visions of an invisible cosmic web, a universe suffused with an unseen substance that dances to the tune of gravity. And let us dream of the day when we will finally unmask this elusive entity, when we will at last come to know the true nature of the dark matter that binds the cosmos together. For in the end, the story of dark matter is the story of us, of our ceaseless curiosity, our unyielding determination to understand the world around us. It is a tale that has unfolded over decades, and will continue to unfold for decades to come, written in the stars and in the hearts of all who dare to ponder the great mysteries of the universe. Good night, and may your dreams be filled with the wonders of the cosmos. As the Milky Way arcs gracefully overhead, it's tantalizing to imagine that we're not merely gazing through the vast emptiness of space, but rather that all we can see is just the tip of a cosmic iceberg, and that our universe is permeated by a massive invisible scaffolding, a ghostly architecture known as dark matter. For decades, scientists have been on a quest to unravel the enigma of this hidden substance, a material that appears to be simultaneously everywhere and yet nowhere to be found. It's a mystery that has captivated some of the greatest minds in astronomy and physics, each working tirelessly to shine a light on the unseen. One of the most significant turning points in this ongoing story came in the early 1980s with the groundbreaking work of two astronomers, Margaret Geller and John Huchra. At the time, our understanding of the large-scale structure of the universe was still in its infancy. Cosmologists had theoretical models suggesting that galaxies might be distributed in a vast web-like pattern, but empirical evidence was lacking. Geller and Huchre set out to change that. Working at the Harvard-Smithsonian Center for Astrophysics, they embarked on an ambitious project to create a comprehensive map of the cosmos. It was a daunting task, requiring them to painstakingly measure the distances to thousands of galaxies using the redshift survey. Night after night, they would point their telescope at a small patch of sky, carefully recording the light from each faint, distant galaxy. As their data grew, a remarkable picture began to emerge. When Geller and Huchre plotted the positions of the galaxies in three-dimensional space, they saw something extraordinary. The galaxies were not randomly scattered, but instead appeared to be arranged in a complex network of filaments, sheets, and voids, a structure that would come to be known as the cosmic web. It was a staggering discovery, one that fundamentally reshaped our understanding of the universe's architecture. But it also raised profound questions. Computer simulations showed that for the cosmic web to form and evolve in the way that Geller and Huchre had observed, there needed to be significantly more matter present than could be accounted for by the visible galaxies alone. In other words, the cosmic web itself seemed to be further, compelling evidence for the existence of dark matter, an invisible substance providing the gravitational scaffolding upon which the visible universe was draped. It was a striking illustration of how dark matter wasn't just influencing the motions of individual galaxies, but was playing a crucial role in shaping the very largest structures in the cosmos. As news of Geller and Huchre's findings spread through the astronomical community, it sparked a wave of excitement and further research. Other teams set out to map even larger volumes of space, using increasingly sophisticated telescopes and computational techniques. Each new survey added detail and richness to the picture of the cosmic web, reinforcing the idea that dark matter was not just real, but was a dominant component of the universe. Yet even as the evidence for dark matter's existence grew more compelling, the question of its fundamental nature remained frustratingly elusive. What exactly was this invisible substance? What was it made of? How did it interact, or fail to interact, with normal matter and energy? These were the questions that would drive the next phase of dark matter research, a quest to move beyond mapping its gravitational influence and to instead directly detect and characterize the particles that comprised it. It was a challenge that would push the boundaries of experimental physics, requiring the construction of incredibly sensitive detectors, often placed deep underground to shield them from the constant rain of cosmic rays and radiation at the Earth's surface. And it would draw in a new generation of scientists, each driven by the tantalizing possibility of being the first to directly glimpse the universe's hidden mass. Among them was Elena April, a physicist at Columbia University who had become fascinated by the dark matter mystery. In the late 1990s, April began developing a new type of detector, known as a liquid xenon time projection chamber. The basic idea was to create a large volume of ultra-pure liquid xenon, maintained at a temperature of -95 degrees Celsius, and to watch for the telltale flashes of light that would be produced if a dark matter particle collided with a xenon atom. It was an extraordinarily difficult technical challenge. The xenon needed to be purified to an almost unimaginable degree, with concentrations of contaminants reduced to less than 1 part per trillion. The detectors needed to be shielded from even the tiniest amounts of background radiation, requiring them to be placed in specialized underground laboratories. And even with all of these precautions, the expected rate of dark matter interactions was still vanishingly small. Perhaps just a handful of events per year, in even the largest detectors. Undeterred, April and her team pressed on. In 2002, they successfully built and operated a 15-kilogram liquid xenon detector, a major milestone, but still far too small to have a realistic chance of detecting dark matter. Over the next decade, they continued to refine and scale up their design, ultimately constructing a massive 3-ton detector known as Xenon 1T. Housed deep beneath a mountain in central Italy, Xenon 1T represented the state-of-the-art in dark matter detection. Its enormous liquid xenon target, coupled with an array of ultra-sensitive photomultiplier tubes, gave it an unparalleled sensitivity to even the rarest and most subtle of interactions. If dark matter particles were out there, and if they interacted with normal matter in the way that most theories predicted, then Xenon 1T stood a good chance of finally detecting them directly. But as the instrument began its long vigil in the quiet depths of the Gran Sasso National Laboratory, the universe seemed to be holding its secrets close. Month after month, the data flowed in, a steady stream of measurements, each one representing a tiny slice of the cosmos, a minuscule sampling of the invisible sea of dark matter that was thought to suffuse the galaxy. And yet, as the data was analysed and scrutinised, no clear signal emerged. There were hints, tantalising glimpses of what might have been dark matter interactions, but nothing definitive. It was as if the dark matter, so dominant on cosmic scales, was somehow managing to remain just beyond our grasp, always one step ahead of our most sensitive detectors. For April and her colleagues, it was a frustrating outcome, but not an entirely unexpected one. They knew that the search for dark matter was always going to be a long game, requiring patience, perseverance, and a willingness to keep pushing the boundaries of what was technologically possible. Even a null result was valuable, helping to constrain the range of possible dark matter particles and interaction cross-sections. And so, as Xenon 1T continued its silent watch, the search for dark matter expanded on other fronts as well. New detectors were proposed and constructed, each one pushing the limits of sensitivity and scale, from the depths of abandoned gold mines in South Dakota to the frigid caverns carved into the Canadian shield. Scientists continued their patient vigil, always listening, always watching for that first, elusive whisper of the universe's hidden mass. As the decades have stretched on, the mystery of dark matter has only seemed to deepen. Despite the best efforts of generations of scientists, its fundamental nature remains unknown. We can map its distribution on vast cosmic scales, we can see its gravitational fingerprints in the motions of stars and galaxies, but its intimate details continue to elude us. And yet, the quest goes on. Driven by curiosity, by the thirst for understanding, and by the tantalizing lure of discovery, scientists continue to probe the darkness, to devise ever more ingenious ways of teasing out its secrets. It is a slow and often frustrating process, marked by false starts and dead ends, but also by moments of incredible insight and beauty. Because in the end, the story of dark matter is really the story of us, of our unending fascination with the cosmos, and our relentless drive to make sense of our place within it. It is a tale that stretches back to the very beginning of modern astronomy, and one that will likely continue for generations to come. And so, as we drift off to sleep beneath the slowly turning sky, we can take comfort in the knowledge that, out there, in the quiet depths of laboratories and observatories around the world, the search continues. That even in the darkest reaches of the cosmos, there is always something new to discover, some fresh mystery to unravel. The universe may keep its secrets close, but we will never stop seeking them out, guided by the stars and by the enduring human desire to know and to understand. And perhaps one day, in some distant future, we will finally pierce the veil and the dark matter will be dark no more. But until then, we can only keep watching, keep wondering, and keep dreaming of the revelations yet to come. As we ponder the vastness of the cosmos, our minds can't help but be drawn to one of its most enduring and captivating mysteries, the puzzle of dark matter. For nearly a century now, this invisible substance has permeated our universe, weaving its way through galaxies and clusters, leaving subtle but unmistakable clues to its presence. And yet, despite the tireless efforts of brilliant scientists across generations, dark matter continues to elude our direct detection, remaining a shadowy enigma that beckons us to unravel its secrets. Among the most diligent seekers of this cosmic mystery was the remarkable Vera Rubin, an astronomer whose groundbreaking observations in the 1970s provided some of the most compelling evidence for dark matter's existence. Night after night, Rubin would ascend into the serene darkness of the Kitt Peak National Observatory, nestled high in the Arizona mountains. There, she would train her keen eye and sensitive instruments upon the graceful spiral galaxies pirouetting through the void, meticulously measuring their rotational speeds. As Rubin carefully analysed her data, a startling pattern began to emerge. The stars and gas at the edges of these galaxies were orbiting far too quickly. their speeds defying the gravitational pull of the visible matter alone. It was as if some unseen presence was providing an extra gravitational boost, keeping these fast-spinning stars from flying off into the void. Rubin's findings built upon the earlier work of Fritz Zwicky, who had noticed similar discrepancies in the motions of galaxies within clusters back in the 1930s. Together, their observations painted a compelling picture. There must be some form of invisible dark matter permeating these galaxies, providing the missing gravitational glue. As the evidence for dark matter continued to mount, cosmologists began to envision our universe as a vast cosmic web, with dark matter serving as the invisible scaffolding upon which galaxies and clusters assembled over billions of years. This vision was stunningly confirmed by the work of Margaret Geller and John Huchra in the 1980s, two astronomers who embarked upon an ambitious quest to map the large-scale structure of the cosmos. Geller and Huchra's journey took them to the Harvard Smithsonian Center for Astrophysics, where they would spend countless hours peering through the eyepiece of the 60-inch Tillinghast telescope. With meticulous care, they measured the distances to thousands of galaxies, each observation a tiny pinprick of light, adding to an emerging tapestry of cosmic structure. As their map took shape, a breathtaking sight unfolded. Galaxies were not scattered randomly throughout the universe, but rather clustered along vast filaments, separated by gaping voids hundreds of millions of light-years across. This awe-inspiring cosmic web, traced out by the patient work of Geller, Huchra, and their collaborators, could only have taken shape if some unseen dark matter had provided the gravitational framework upon which galaxies coalesced and grew. Computer simulations demonstrated that without dark matter's invisible hand, the universe would appear far more uniform, lacking the elegant filamentary structure that we observe today. And so, the hunt for dark matter's identity shifted into high gear, as physicists and astronomers sought to unmask the elusive particle or particles that could explain its gravitational influence. Leading the charge in this quest are researchers like Elena April and Laura Bordis, who have devoted their careers to designing and building incredibly sensitive detectors, capable of registering the faint whisper of a dark matter particle colliding with an atom of normal matter. Deep beneath the Earth's surface, shielded from the ceaseless rain of cosmic rays that bombard our world, these detectors wait with patient vigilance for a telltale signal. Ensconced within chambers of purified liquid xenon, cooled to a frigid -100 degrees Celsius, they stand as silent sentinels, ready to capture the rare kiss of a dark matter particle against a xenon nucleus. For April, Bordis, and their fellow researchers, each day brings the possibility of a groundbreaking discovery, a long-awaited glimpse into the true nature of this perplexing cosmic constituent. Yet even as these dedicated scientists press forward, the spectre of doubt still lingers at the edges of our understanding. Some researchers, grappling with the persistent elusiveness of dark matter particles, have begun to explore alternative explanations for the gravitational effects we attribute to this invisible substance. Modified theories of gravity, which attempt to explain galaxy and cluster dynamics without invoking new forms of matter, have gained traction in some circles, sparking lively debates at conferences and in the pages of scientific journals. But for now, the prevailing view among experts is that dark matter remains our best solution to the puzzles left behind by Zwicky, Rubin, and others. Its invisible threads appear to be woven into the very fabric of our cosmos, from the smallest dwarf galaxies to the grandest superclusters. Dark matter played a crucial role in the formation and evolution of cosmic structure, providing the gravitational seeds around which the luminous universe blossomed over billions of years. And so, as we drift off to sleep beneath the twinkling tapestry of the Milky Way, we are left to ponder the great unfinished story of dark matter. For all that we have learned about its effects and distribution, so much remains shrouded in uncertainty. Is it made of a single particle species, or an entire family of exotic substances? Does it interact with itself, or with normal matter in ways beyond gravity? Might it hold the key to even deeper mysteries like the nature of dark energy or the ultimate fate of our universe? These are the questions that continue to drive the tireless efforts of astronomers and physicists around the globe, united in their determination to shed light on the dark cosmos. From the mountaintop observatories where Vera Rubin once gazed skyward, to the underground laboratories where Elena April and Laura Bordis listened patiently for a whisper of dark matter, the quest to solve this enduring enigma forges ahead. And as we entrust ourselves to the embrace of sleep, our dreams carry us to the edge of the unknown, to a universe suffused with an ethereal cosmic web, spun from the invisible threads of dark matter. In our mind's eye, we can trace the intricate dance of galaxies along these filaments, marvelling at the unseen forces that shape the grandest structures of the cosmos. Though the true nature of dark matter may still elude us, its mystery continues to captivate our imaginations, inspiring us to ponder the profound depths of the universe we call home. So let's drift off into the soothing darkness, our thoughts filled with the wonders of the cosmos and the enduring quest to illuminate its shadows. For in the grand tapestry of the universe, dark matter weaves a captivating tale, one that began with the first glimpses of unseen influences and continues to unfold with each new discovery and each unanswered question. As we surrender to the tranquility of sleep, we can take comfort in knowing that the story of dark matter and our place within it is still being written, one observation and one dream at a time. As we gaze up at the tranquil night sky, it's hard to imagine that some of the most dramatic events in the cosmos are playing out before our very eyes. Supermassive black holes billions of times more massive than our sun, swallowing up stars and gas with wild abandon. Enormous jets of high-energy particles streaming out at nearly the speed of light, stretching for thousands of light years. Brilliant flashes marking the explosive deaths of massive stars. And yet, the violence and turmoil out there in the universe pales in comparison to a far greater mystery, one that is everywhere around us and in us, yet invisible and nearly undetectable. This is the enigma of dark matter, a shadowy substance that outweighs all the normal matter we can see by a factor of 6 to 1. A cosmic elephant in the room that has gravitationally shaped the evolution of the entire universe and continues to guide the majestic ballet of the galaxies. For nearly a century now, the dark matter mystery has captivated some of the greatest scientific minds. Astronomers who first noticed that the universe was behaving quite oddly, particle physicists searching for its elusive fundamental building blocks, and cosmologists tracing its influence back to the earliest ages of the universe. Each made profound contributions that brought us closer to the truth, while revealing just how much more there was to discover. Perhaps no one was more instrumental in exposing the first tantalizing clues of dark matter than the brilliant and irascible Fritz Zwicky. Born in Bulgaria in 1898 and raised in Switzerland, Zwicky's bold ideas and abrasive personality would often put him at odds with the scientific establishment. But his tenacious pursuit of the truth and his keen physical insights repeatedly led him to revolutionary discoveries. In the early 1930s, as a young professor at Caltech, Zwicky turned his attention to the motions of galaxies in the nearby Coma cluster. By meticulously measuring their speeds, he could use basic physical principles to estimate the total gravitational mass of the cluster. But when he did the calculation, he arrived at a startling conclusion. The cluster seemed to weigh over 400 times more than could be accounted for by the visible galaxies alone. Zwicky boldly proposed that the cluster must be suffused with some kind of unseen Dunkel materie, dark matter, that provides the extra gravitational glue. His astonishing claim was met with great skepticism and was largely ignored by the astronomical community. But over the next few decades, as more clusters were surveyed, the evidence mounted that Zwicky was onto something profound. Meanwhile, other astronomers were uncovering their own strange observations closer to home. In the 1960s and 70s, Vera Rubin and Kent Ford of the Carnegie Institution meticulously measured the rotation speeds of dozens of spiral galaxies, including our own Milky Way. According to the laws of gravity, the stars and gas in the outskirts of a spiral should orbit more slowly than material near the centre. But Rubin and Ford found instead that the rotation speeds stay remarkably constant, all the way out to great distances. Once again, some unseen mass seemed to be providing extra gravity, flattening out the rotation curve. And this dark matter couldn't just be in a halo surrounding the galaxy. It had to be distributed throughout the disk itself, mingling with the stars and gas. As the evidence mounted from galaxy motions that dark matter was ubiquitous in the universe, cosmologists were converging on the need for its existence from a completely different line of reasoning. They had long known that the attractive force of gravity should be slowing down the expansion of the universe, but by how much depended critically on the total density of matter. In the early 1980s, by comparing the observed expansion rate with the density of visible matter, they concluded that there must be far more mass in the universe that we can see, about 10 times more. This provided the first glimpse of cosmic concordance. Dark matter could simultaneously explain the motions of galaxies and the dynamics of the universe as a whole. The clincher came later that decade when Margaret Geller, John Huchra, and their collaborators at the Harvard-Smithsonian Center for Astrophysics undertook the most ambitious mapping of the large-scale structure of the universe ever attempted. Using a custom-built spectrograph on a telescope in Arizona, they worked tirelessly for years to measure the distances to thousands of galaxies. When they plotted the galaxies in 3 dimensions, a remarkable pattern emerged, a vast cosmic web with enormous filaments and sheets separated by gaping voids. The structure stretched for hundreds of millions of light-years, far larger than any single galaxy or cluster. But most striking of all was its sheer fragility. Such gossamer filaments could never have survived the gravitational pull of all the matter within them. Computer simulations soon demonstrated that this majestic architecture could only form and survive if the universe was suffused with dark matter, about 5 times more abundant than normal matter. This invisible scaffolding would provide the gravitational framework for the normal matter to condense into galaxies and clusters, while holding the cosmic web together. By the 1990s, the dark matter paradigm was firmly established. The evidence from galaxy motions, cosmic expansion, and large-scale structure all pointed to the same conclusion, that over 80% of the matter in the universe was dark and unknown. The race was on to identify the particles that made up this mysterious substance. Dozens of experimental groups around the world began building increasingly sensitive detectors to try to catch the rare interactions between dark matter particles and normal matter. Leading the charge were physicists like Elena April of Columbia University, Laura Bordis of the University of Zurich, and their international collaborators. Their detectors were marvels of precision engineering, ultra-pure tanks of liquid xenon or germanium crystals, cooled to near absolute zero and shielded deep underground from the constant rain of cosmic rays. They realized that dark matter particles must be electrically neutral and non-interacting, able to pass effortlessly through normal matter. Calculations suggested they might be weakly interacting massive particles, WIMPs, with masses dozens to thousands of times that of a proton. When a dark matter particle collided with an atomic nucleus in their detector, it should produce a tiny flash of light and a slight vibration, but such signals would be incredibly faint and easily swamped by background contamination. To catch them, the detectors had to be pristine and the event rates infinitesimal, perhaps just a handful of candidate events per year. As the experiments grew more sensitive, they began to close in on the possible mass ranges and interaction strengths of dark matter particles. But to their surprise and frustration, detection remained maddeningly elusive. Huge swaths of parameter space were excluded, forcing theorists to concoct ever more exotic dark matter models. A few tantalizing signals emerged, hinting at a possible discovery, but none could be confirmed definitively. The absence of a smoking gun particle forced some theorists to question the dark matter paradigm itself. Perhaps the strange behavior of galaxies and the cosmos was not due to an invisible substance, but to a breakdown of gravity on the larger scales. Maverick theories like modified Newtonian dynamics, MOND, and tensor vector scalar gravity, TeVS, struggled valiantly to reproduce the observations without invoking dark matter. But even the most successful of these alternative theories could not match the exquisite agreement between dark matter simulations and the observed universe. The cosmic microwave background, the relic heat of the Big Bang, bore the unmistakable imprint of a dark matter in its mottled pattern of hot and cold spots. The gravitational dance of colliding galaxy clusters, like the iconic Bullet cluster, could only be explained if dark matter were stripped away from the luminous gas during the collision. And so, after nearly a century of searching, the dark matter mystery endures. We have come astonishingly far in tracing its influence across the cosmos and in narrowing down the possibilities for its fundamental nature, but its particle identity remains stubbornly hidden, its true essence still cloaked in shadow. Perhaps the coming years will finally bring a breakthrough. the long-awaited direct detection of a dark matter particle in the lab, or the creation of dark matter at a particle collider. Or perhaps dark matter will continue to elude us, forcing us to question our most cherished notions of the nature of matter, gravity, and the universe at the deepest levels. But one thing is clear. The story of dark matter is one of the great scientific adventures of our time, and a reminder of just how much we have yet to learn about the cosmos we call home. As we drift off to sleep, let us dream of the wonders that still lie hidden in the darkness, waiting to be illuminated by the tireless seekers of the unknown. Quietly, we end our journey for tonight, our minds filled with the enigma of dark matter. The stars twinkle gently overhead, their light traversing unimaginable distances through the invisible cosmic web that binds the universe together. We may not yet know the identity of the dark matter that weaves this grand structure, but we can marvel at the ingenuity and perseverance of the scientists who first glimpsed its presence and who continue to pursue it to the very edges of human knowledge. In the calm stillness of the night, we are left with a profound sense of the vastness and mystery of the cosmos and the enduring human quest to unlock its deepest secrets. As we ponder the enduring mystery of dark matter, our minds may drift to another pivotal figure in this cosmic detective story, the brilliant and tenacious Vera Rubin. In the late 1960s and 70s, Rubin was a researcher at the Carnegie Institution in Washington, quietly revolutionizing our understanding of galaxies and the hidden matter they contain. Night after night, Rubin and her colleague Kent Ford would ascend the winding road, leading up to the domed observatory perched atop Kitt Peak in Arizona. Inside the cavernous dome, the still air would be punctuated only by the low hum of electronics and the occasional whir of the telescope's motor as they guided it toward their targets, distant spiral galaxies spinning silently against the inky black sky. Peering through the eyepiece, Rubin and Ford meticulously measured the rotational speeds of stars at different distances from the centers of these galaxies. The data they collected would soon upend conventional wisdom about how galaxies behaved. According to the laws of physics, stars and gas in the outer reaches of a spiral galaxy should orbit more slowly than material closer to the dense galactic center, just as the outer planets in our solar system revolve more slowly than those near the Sun. The visible matter in the outskirts of a galaxy shouldn't have the gravitational heft to keep up with the pace of inner regions. But that's not what Rubin and Ford found. To their amazement, the outer parts of galaxies were rotating just as quickly as regions closer to the center. The implications were staggering. Some unseen form of matter must be providing the additional gravitational glue to hold these fast-spinning galaxies together. Rubin would later recall the sheer excitement of those early findings, saying, "If I could have my pick of how to die, it would be at the telescope." As Rubin and Ford published their groundbreaking results, the wider astronomical community began to take serious notice. Other researchers started carefully measuring the rotational speeds of dozens of additional galaxies, and the results were always the same: flat rotation curves that could only be accounted for if galaxies were immersed in vast, invisible halos of what Rubin called dark matter. These remarkable discoveries earned Vera Rubin a number of prestigious awards and a reputation as one of the most insightful astronomers of her generation. And yet, recognition from the Nobel Committee would elude her. Many in the scientific community expressed shock and disappointment that her paradigm-shifting work on dark matter wasn't honoured with a Nobel Prize in Physics before her passing in 2016. Astronomer Emily Levesque captured the sentiments of many, writing that the existence of dark matter has utterly revolutionized our concept of the universe and our entire field. The ongoing effort to understand the role of dark matter has basically spawned entire subfields within astrophysics and particle physics at this point. Alfred Nobel's will describes the Physics Prize as recognizing the most important discovery within the field of physics. If dark matter doesn't fit that description, I don't know what does. Though she may not have received that ultimate scientific accolade, there is no doubt that Vera Rubin's rigorous observations and brilliant insights launched a new era in cosmology. Her work elevated dark matter from a tentative hypothesis to a central pillar of modern astronomy, and the mystery she helped uncover, the invisible cosmic scaffolding that binds galaxies and the universe itself together, continues to captivate and inspire scientists around the world today. As we lie here in the darkness, our eyes heavy with sleep, we can almost imagine Rubin at the telescope on one of those long Kitt Peak nights, her eyes sparkling with each new data point confirming the existence of something unseen and extraordinary. Through her work and the efforts of so many others, we're reminded that some of the most wondrous discoveries are those that reveal how much we still have yet to learn about the cosmos we call home. The quest to understand dark matter is far from over. With every passing year, new generations of ever more sensitive detectors are deployed deep underground, quietly waiting for the subtle signal of a dark matter particle colliding with an atomic nucleus. Powerful particle colliders smash together subatomic shards of matter at nearly the speed of light, watching for hints of dark matter particles among the detritus. And astronomers continue to study the motions of stars and galaxies with increasing precision, mapping the gravitational influence of dark matter at immense scales. Like a cosmic game of hide-and-seek, dark matter has proven elusive quarry. But scientists remain undeterred, propelled by the same spirit of relentless curiosity that drove Vera Rubin and her predecessors to spend so many long nights at the telescope, teasing out the secrets of the universe. Perhaps someday, decades or even centuries from now, a future scientist will finally unlock the mystery, identifying the particles that make up the dark matter suffusing our cosmos. Or perhaps dark matter will prove to be something even stranger, a gateway to entirely new realms of physics that we have yet to imagine. But for now, as we drift off to sleep, we can marvel at the fact that we are part of a cosmos that is vast, ancient and full of wonders both seen and unseen. The stars wheeling silently overhead, the galaxies pinwheeling through the inky depths, and the dark matter enveloping it all. A reminder of how much beauty and mystery there is yet to uncover in the universe we share. So let us embrace the darkness as we slip into our dreams, knowing that the quest for understanding will continue long after we wake. The story of dark matter is still being written, one observation and one sleepless night at a time, by all those who keep watch over the cosmos. And though the journey ahead may be long, the destination, a deeper understanding of the very fabric of reality, is surely worth the pursuit. Good night, and may your dreams be filled with the wonders of the unseen universe. As we've seen, dark matter has defied our efforts to unmask it for nearly a century. Yet those decades of astronomical observations, painstaking calculations, and cosmic cartography have painted a vivid picture of its essential role in the universe we inhabit. Though invisible, dark matter appears to suffuse the cosmos, guiding the formation and motions of galaxies and galaxy clusters. It provided the gravitational scaffolding for the vast web-like structure mapped by Margaret Geller, John Huchra and others. A colossal architecture spanning billions of light years, with immense filaments and yawning voids. All along those filaments, dark matter seems to cradle galaxies and draw them into majestic, slowly wheeling dances. Even as we picture this grand cosmic ballet, we have to marvel at its still hidden choreographer. After all these years, the true nature of dark matter remains an enigma. Is it some new, elusive particle that flits ghost-like through the universe, imperceptible except through its gravitational influence? Physicists have dreamed up a whole stable of potential dark matter particles over the years, things like axions, sterile neutrinos, and the perennial favourite, weakly interacting massive particles or WIMPs, but so far even our most sensitive detectors have failed to catch them directly. The quest to unmask the dark matter particle has taken on an almost mythic quality, like some scientific Moby Dick. Researchers like Elena April and Laura Beodis lead dedicated teams in the pursuit, deploying ever more sophisticated traps in the hopes of glimpsing their quarry. Imagine their experiments: multi-ton vats of liquid xenon or supercooled crystals of germanium, tucked away in deep underground caverns and shielded by kilometres of earth and rock from the ceaseless rain of background radiation. They wait with the patience of Penelope, hoping for a single telltale flash in their detectors, heralding a long-awaited collision between dark and luminous matter. Yet as the years tick by without a definitive sighting, some astronomers and physicists have begun to wonder if we've been charting a course for the wrong whale. A few have proposed alternative explanations for the observed gravitational effects, things like modified theories of gravity that might make dark matter unnecessary. But for most experts, dark matter remains the most compelling model, even in the face of its continued elusiveness. There's something strangely poetic in the notion that the substance suffusing our universe is so maddeningly difficult to behold. As we lie here in the dark, drifting towards sleep, it's calming to contemplate the dark cosmos drifting along with us. For all our knowledge, for all the power of our scientific instruments and theories, there is still so much mystery woven into the fabric of existence. The story of dark matter reminds us of that humbling fact. Here we are, on a little island of light and life, embedded in a vast ocean of unseeable, unknowable stuff. It tugs on our galaxy and binds our universe together, an invisible but essential thread in the cosmic tapestry. One day, perhaps, a vigilant researcher will glimpse a long-sought flash in a detector, or an innovative new theory will unveil the cosmos in a fresh light, and the veil shrouding our dark cosmic companion will finally lift. But for now, there is something strangely comforting in the mystery. In a universe as ancient and immense as ours, there is ample room for wonder, ample space for the unknown. Dark matter, in its invisible pervasiveness, seems almost to embody that limitless cosmic enigma. So as we let ourselves sink into the embrace of sleep, we can allow our minds to wander out into that dark immensity. Let us dream of the great web of galaxies sprawling across the void and the invisible meshwork of matter that binds them. Let us ponder the dedicated researchers working late into the night, patiently waiting and watching for a sign from the dark. And let us marvel at the thought that as we slip into unconsciousness, as our own awareness goes dark, the great wheels of the galaxy continue their ponderous turning, guided by a substance we can sense but never see. There is a strange and wonderful symmetry here, between the darkness of sleep and the darkness of space, the unknown realms within and the unknowable reaches without. In that symmetry, perhaps, we can find a peculiar kind of peace, a calm acceptance of the mysteries that frame our existence. For in a cosmos so shot through with enigmas, a cosmos that hides its dominant constituent in an impenetrable shroud of invisibility, what more natural response is there than humble, wondering awe? And so, as we finally let the night enfold us, let us carry that sense of reverent wonder into our dreams. Let the dark matter that binds the spinning galaxies be a reminder of the profound and primal mysteries that bind us, too, to the great web of being. And let us rest easy in the knowledge that though the dark universe eludes our grasp, it cradles us just the same, in a vast and fathomless embrace. Good night. As we ponder the cosmic web that appears to hold our universe together, we turn our attention to those who have dedicated their careers to illuminating this dark mystery. In hushed tones, they share a common goal: to be the first to unmask the elusive dark matter particle that has defied detection for so long. In the late 20th century, as the evidence for dark matter continued to mount, a new generation of scientists took up the challenge of identifying its source. Among them was Dr. Elena Aprile, a soft-spoken Italian physicist with a steely determination to solve the dark matter riddle. Born in Milan in 1954, Elena was drawn to the mysteries of the universe from a young age. As a child, she would often gaze up at the night sky, marvelling at the stars and wondering what secrets they held. This early fascination with the cosmos would shape the course of her life and career. After earning her PhD in physics from the University of Geneva, Elena joined the faculty at Columbia University in New York City. It was here that she began to focus her research on the search for dark matter particles. In the late 1990s, Elena and her team embarked on an ambitious project to build a new type of detector that could catch the faint whispers of dark matter interactions. They called it xenon, named after the liquid xenon that would fill its heart. Xenon, a noble gas, has a unique property that makes it ideal for dark matter detection. When a particle collides with a xenon atom, it produces a tiny flash of light and a few free electrons. By carefully measuring these signals, Elena and her colleagues hoped to identify the telltale signs of a dark matter interaction. But to have any hope of success, the xenon detector would need to be shielded from the constant bombardment of cosmic rays and background radiation that showers down on Earth's surface. So Elena and her team went underground, deep beneath the mountains of central Italy. In a cavernous laboratory carved out of solid rock, they began to assemble their dark matter hunter. The detector itself was a marvel of engineering, a complex array of sensors and electronics surrounding a large tank of liquid xenon, all encased in layers of shielding to block out any unwanted noise. As the first coolant began to flow and the xenon liquefied, Eleanor and her colleagues held their breath. Would the detector work as planned? Would it be sensitive enough to catch the ethereal whispers of dark matter? Days turned into weeks, and weeks into months. The team worked around the clock, fine-tuning the detector and analysing the data streaming in from its sensors. But despite their best efforts, the dark matter particle remained elusive. Eleanor refused to be discouraged. She knew that the search for dark matter was a marathon, not a sprint. With each passing year, she and her team continued to refine their methods and upgrade their equipment, pushing the boundaries of what was possible. As the new millennium dawned, the Xenon collaboration had grown to include hundreds of scientists from around the world. Together, they built ever larger and more sensitive detectors, each one a technological marvel in its own right. From her underground lab in Italy, Elena watched as her life's work took on a momentum of its own. She marvelled at the dedication and ingenuity of her colleagues, united in their quest to solve one of the greatest mysteries of the cosmos. Yet even as the xenon detectors grew in size and sophistication, the dark matter particle continued to elude them. With each passing year, Eleanor and her team set new records for sensitivity, probing ever smaller cross-sections of possible dark matter interactions. But still, the data remained stubbornly silent. As she entered her 7th decade, Eleanor began to ponder the possibility that she might not live to see the dark matter mystery solved. But even in the face of this sobering realization, she remained undaunted. For Elena, the search for dark matter had never been about personal glory or recognition. It was about the thrill of discovery, the joy of unravelling the secrets of the universe. And so she pressed on, driven by an unshakable belief that the answer lay just beyond the next horizon. With each new detector, each new analysis, she and her colleagues were pushing back the boundaries of human knowledge inch by hard-fought inch. As we lie here in the darkness, our minds adrift in the vastness of the cosmos, we can take comfort in the knowledge that scientists like Elena Aprile are out there, quietly toiling away in their underground labs, driven by a passion for discovery and an unquenchable thirst for knowledge. Theirs is a quest that may span generations, a search for an elusive particle that holds the key to understanding the very fabric of our universe. And though the road ahead may be long and winding, we can rest assured that they will never give up, never stop pushing forward, until at last the dark matter is dragged into the light. So let us drift off to sleep now, our dreams filled with the wonder and mystery of the cosmos. And let us give thanks for the tireless efforts of those who have dedicated their lives to illuminating the darkness one particle at a time. As we ponder the grand cosmic web that seems to connect the universe, it's natural to wonder about the visionaries who first glimpsed its structure. In the 1980s, 2 astronomers embarked on an audacious quest to map the large-scale arrangement of galaxies, a project that would ultimately transform our understanding of the cosmos. Margaret Geller and John Huchra were unlikely scientific partners. Geller was a young researcher at the Harvard-Smithsonian Center for Astrophysics, with a keen interest in the distribution of galaxies. Huchra, nearly a decade older, was an established astronomer at the same institution, known for his work on measuring the expansion rate of the universe. Together, they set out to create the most comprehensive map of the cosmos ever assembled. Night after night, Geller and Huchra would aim the 60-inch telescope at Mount Hopkins in Arizona at the sky, meticulously measuring the distances to thousands of galaxies. It was painstaking work, requiring long hours of observations and careful analysis. But as their data accumulated, a striking pattern began to emerge. Rather than being evenly distributed, the galaxies seemed to be arranged in a vast network of filaments, with immense voids in between. It was as if the universe was structured like a colossal sponge, with galaxies clustering along the edges of the voids. This was a far cry from the smooth, uniform cosmos that many astronomers had envisioned. As Geller and Huchra's map grew to include over 18,000 galaxies, spanning a significant portion of the observable universe, the reality of this cosmic web became undeniable. Their groundbreaking work, published in a series of landmark papers, provided the first clear evidence of the large-scale structure of the universe. But the discovery of the cosmic web also deepened the mystery of dark matter. computer simulations showed that in order for such a web-like structure to form, there had to be a significant amount of additional unseen matter providing the gravitational scaffolding. The visible galaxies alone were not enough to explain the observed arrangement. In a sense, Geller and Huchra's map was not just a chart of galaxies, but a map of dark matter's hidden influence. Wherever there were galaxies, there had to be significant concentrations of dark matter holding them together. And in the voids between the filaments, dark matter was still present, but more diffusely spread out. The realization that dark matter played a central role in shaping the large-scale structure of the universe added new urgency to the quest to understand its nature. If this invisible substance was so crucial to the cosmos's architecture, then unmasking its identity became one of the most pressing problems in modern astronomy. As Geller and Huchra's cosmic web became widely accepted, astronomers began to speak of the universe as a dark matter scaffolding, upon which the luminous galaxies were draped like sparkling jewels. It was a poetic image, but one that underscored our ignorance. For all the beauty and intricacy of the visible universe, it was merely a trace element in a much vaster, unseen cosmic edifice. In the decades since Geller and Huchra's pioneering work, astronomers have continued to refine our map of the universe. With each new survey, the cosmic web comes into clearer focus, its filaments and voids delineated with ever greater precision. Yet the dark matter that suffuses this structure remains stubbornly invisible, detectable only by its gravitational influence. As we lie beneath the night sky, gazing up at the stars, it's humbling to remember that we are seeing only a small fraction of what's truly there. The universe we inhabit is one of luminous galaxies embedded in a far larger cosmos of dark matter and dark energy. It is a universe of astonishing beauty and staggering mystery, one that continues to challenge our understanding and fuel our curiosity. And so the quest to understand dark matter continues, carried forward by generations of scientists who share Geller and Huchra's passion for mapping the unknown. With each new observation and each new theory, we inch closer to grasping the true nature of the dark cosmos. But for now, as we drift off to sleep, we can marvel at the vastness of the universe and the enduring enigmas it contains, knowing that the story of dark matter is still being written in the silent depths of space. As the cosmic web stretches out across unimaginable distances, you might drift off to sleep picturing the vast filaments and voids it traces through the universe. Those vast structures, born in the early moments after the Big Bang, have evolved over billions of years under the influence of dark matter's unseen gravitational guidance. The evolution of cosmic structure is one of the key reasons most scientists believe dark matter must exist. Modern supercomputer simulations of the universe show that without the gravitational influence of dark matter, we simply can't explain how the large-scale structures we observe today could have formed. Starting from the tiny quantum fluctuations in density left over from the Big Bang, these simulations apply our understanding of physics and watch the model universe evolve over billions of years. With normal matter alone, gravity would be too weak to pull together the majestic filaments, galaxies and galaxy clusters that fill our real universe. But add in dark matter with about 5 times the abundance of normal matter, and suddenly the simulated cosmos begins to look uncannily like the real one. One of the pioneers in this type of cosmic simulation was Margaret Geller's collaborator John Huchra. Together, Geller and Huchra laboured for over a decade to map the large-scale structure of the nearby universe, revealing the great cosmic web for the first time. But Huchra was also fascinated by how that structure came to be. In the late 1980s, he began working with colleagues to simulate the growth of cosmic structure in a supercomputer model, starting from the afterglow of the Big Bang, and watching it evolve over billions of virtual years into a tangled web of filaments and voids that looked remarkably like what he and Geller had discovered. Today, cosmic structure simulations have grown vastly in scale and sophistication, modelling trillions of dark matter particles and the complex cosmic weather of gas dynamics that shape galaxies and galaxy clusters. But they still tell the same basic story. Without the gravity of dark matter, we simply can't explain the universe we see. As you contemplate the invisible skeleton of the cosmos, your eyelids may grow heavier and your mind start to drift. Through the power of physics and supercomputing, scientists can now visualize the unseen, carrying out cosmic evolution in a silicon universe, But as sophisticated as these simulations have become, they're still just models. Dark matter itself continues to elude our telescopes and detectors. The search for the particles that make up dark matter has been going on for decades now, carried out in quiet labs deep beneath the surface of the Earth. Physicists realized early on that dark matter can't be made of any of the known types of particles. It doesn't seem to emit, reflect, or absorb light, and it passes right through normal matter without a trace. Somehow, across billions of years, it has refused to interact with the stuff we're made of in any way except through gravity. So to catch such a stubbornly aloof particle, physicists have had to dream up some very clever traps. The basic idea is simple. Build a detector out of some very pure, stable material, cool it down to very low temperatures to minimize background noise, and then patiently wait for the ping of a dark matter particle bumping into one of the detector's atoms. But if dark matter particles are as weakly interacting as physicists believe, then these collisions should be exceedingly rare. To shield their sensitive detectors from the constant rain of cosmic rays and particles of normal matter zipping around, dark matter hunters have to set up their experiments deep underground, in old mine shafts or beneath mountains. Even with these precautions, the expected signal is so faint that it could take years of patient waiting to detect just a few precious events. It's the sort of work that requires a special kind of dedication and quiet focus. Many of the leading figures in this field have spent their entire careers in pursuit of dark matter, with no guarantee of success. One of these dedicated researchers is Italian physicist Elena April, who leads the Xenon dark matter experiment nearly a mile underground in central Italy. April has been on the hunt for these elusive particles since the 1990s, through a series of ever more sensitive detectors. The Xenon detector uses a tank of ultra-pure liquid xenon, cooled to a frigid minus 139 degrees Fahrenheit. If a dark matter particle happens to collide with the xenon nucleus, it should produce a faint flash of light and a few free electrons which the detector can pick up. But even with 3.5 tons of liquid xenon and nearly a mile of solid rock to screen out unwanted noise, the signal April is looking for is incredibly faint. In one recent one-year run, the xenon detector recorded just 53 Candidae events, and even those are probably mostly due to background noise rather than dark matter. Still, with each new iteration of the experiment, April and her team are pushing back the boundaries of the unknown, narrowing down the possible characteristics of dark matter. And xenon is just one of several next-generation dark matter experiments using similar strategies. Others, like the Lux Zeppelin experiment in South Dakota, are looking for the same faint flashes in tanks of liquid xenon. The ADMX experiment, in an underground lab in Washington state, uses superconducting magnets to try to convert dark matter particles into detectable radio waves, and the PICO experiment, buried in a Canadian mine shaft, uses superheated bubbles in a jar of fluorinated liquid to sense the tiny vibrations of a dark matter collision. As you start to drift off, you might picture these dedicated researchers in their quiet underground labs, watching their delicate detectors with a combination of patience and stubborn hope. Through decades of careful work, they've managed to rule out many of the most promising ideas about what dark matter might be, but still, the answer eludes them. It's the sort of cosmic mystery that might haunt your dreams as your sleeping mind tries to wrap itself around the idea of an invisible substance far more abundant than all the normal matter in the universe, an ethereal sea of particles flooding through you at every moment, holding together the galaxies and the great cosmic web, and yet somehow beyond our grasp. As your thoughts grow more diffuse and sleep starts to take hold, you might find some strange comfort in that idea, that even in our age of cosmic simulations and precision physics, there is still room for wonder, for mystery, that the universe we inhabit is still, in many ways, a profoundly strange and beautiful place. The search for dark matter reminds us of the great human capacity for curiosity and determination in the face of the unknown. Like so many of the most profound scientific quests, it may not have an end in sight. But the story of that quest is a deeply human one, filled with all the quiet drama of late nights in the lab, long years of painstaking work, flashes of insight, and an enduring longing to solve one of the deepest mysteries of our universe. As you surrender to sleep at last, the story of dark matter continues, carried forward by an international community of scientists who have devoted their lives and careers to chasing the invisible. They may labour in obscurity far from the limelight, but driven by curiosity and determination, they keep asking one of the most profound questions we know. What is the universe made of? It's a question that may not have a final answer anytime soon, but in our tireless efforts to solve it, we reveal something profound about ourselves. That even in the face of an indifferent universe, our desire to know, to understand, to trace the intricate workings of nature never sleeps. And so the search goes on, through long years and late nights, deep underground and out in the cold night sky. Because as long as we keep following that yearning to solve the mysteries of our universe, we show that there is more to the human story than meets the eye as well. Just as dark matter invisibly guides the great dance of the galaxies, our restless curiosity leads us forever onward into the unknown. As we gaze up at the night sky, it's humbling to realize how little we truly understand about the vast cosmos that surrounds us. The deeper we peer into the universe, the more mysteries we seem to uncover. And perhaps no cosmic enigma has proven more enduring, more captivating than the puzzle of dark matter. For nearly a century now, dark matter has eluded our most determined efforts to unmask its true nature. We can see its gravitational fingerprints everywhere, in the motions of stars and galaxies, in the bending of the light from distant objects, in the very structure of the universe itself. Yet despite making up the overwhelming majority of matter in the cosmos, dark matter remains invisible, intangible, forever slipping through our fingers like cosmic smoke. But the story of dark matter is also a deeply human one. It's a tale of brilliant minds grappling with the unknown, of tireless researchers chasing shadows, of the indomitable spirit of scientific inquiry that drives us to keep probing the darkness in search of answers. So let us embark on a journey through the history of this enduring mystery and meet some of the remarkable figures who have illuminated our path along the way. Our story begins in the early decades of the 20th century, as astronomers were just beginning to unlock the true scale of the universe beyond our own Milky Way galaxy. In 1933, a brilliant young scientist named Fritz Zwicky was studying the motions of galaxies in a massive cluster called the Coma Cluster. What he found would plant the first seeds of the dark matter revolution. Zwicky, a Swiss astronomer working at the California Institute of Technology, was a pioneering figure in the study of galaxies and clusters. With his keen eye and quick mind, he meticulously measured the velocities of galaxies within the Coma Cluster, expecting their motions to follow the laws of gravity as dictated by their visible mass. But to his surprise, the galaxies were moving far too quickly. It was as if some unseen mass was providing extra gravitational pull, holding the speeding galaxies in orbit. Zwicky coined a name for this invisible substance, Dunkelmaterie, or dark matter in English. His calculations suggested that to account for the high velocities he observed, the Coma Cluster must contain far more dark matter than luminous matter. It was a bold claim, and it would take decades for the scientific community to begin to accept the implications. In the 1970s, another groundbreaking scientist picked up the dark matter torch. Vera Rubin, a brilliant American astronomer, had been fascinated by the rotation of galaxies since her days as a graduate student. Together with her colleague Kent Ford, Rubin set out to meticulously measure the orbital speeds of stars within spiral galaxies, hoping to map out the distribution of mass from galactic cores to their outer edges. What Rubin and Ford found sent shockwaves through the astronomical community. In galaxy after galaxy, the orbital velocities of stars remained high, even far from the central hub of visible mass. Just like Zwicky's fast-moving galaxies and clusters, the stars in Rubin's galaxies were moving too quickly to be accounted for by visible matter alone. Imagine the scene. Night after night, Rubin and Ford would train their telescope on target galaxies, carefully recording the spectra of light from stars at varying distances from the galactic centre. With painstaking precision, they would measure the Doppler shifts in the star's light, the telltale signs of their orbital velocities, and time after time the results defied the expected drop-off in speed at greater radii. It was a staggering discovery. Spiral galaxies seemed to be suffused with a vast halo of unseen mass, extending far beyond the luminous regions. Rubin's work provided compelling evidence that dark matter wasn't just a quirk of galaxy clusters, but a ubiquitous presence on galactic scales. The shadows of the cosmos were growing longer. As the 20th century drew to a close, the astronomical community was confronting a profound realization. The visible universe we'd been studying for centuries was just the tip of a vast cosmic iceberg. Wherever we looked, the gravitational influence of dark matter seemed to dominate. But what was this invisible substance exactly? What secrets lay waiting to be revealed? A new generation of scientists took up the challenge of unmasking dark matter as the 21st century dawned. One of the most promising avenues was the search for individual dark matter particles, the elusive building blocks that must make up this invisible cosmic scaffold. Many researchers focused their efforts on designing ultra-sensitive detectors to catch the rare interactions between dark matter particles and normal matter. Leading figures like Eleni April at Columbia University and Laura Bordis at the University of Zurich spearheaded ambitious experiments, burying their detectors deep underground to shield them from interfering radiation. The detectors themselves are marvels of precision engineering. Imagine a tank filled with tons of liquid xenon, cooled to a frigid -100 degrees Celsius. Photomultiplier tubes line the walls, waiting to catch the faintest flashes of light that would signal a dark matter particle colliding with a xenon nucleus. These experiments must be able to sift through billions of interactions to spot the telltale signature of a single dark matter strike. So far, the particles have proven frustratingly elusive. Many well-motivated candidates like weakly interacting massive particles, WIMPs, and axions have been proposed by theorists, but despite decades of searching, none have been conclusively detected. The direct hunt for dark matter continues to push the boundaries of experimental sensitivity, probing ever fainter interactions and lighter particle masses. Meanwhile, astrophysicists have been mapping dark matter's influence on the grandest scales, revealing its central role in the very structure of the universe itself. In the 1980s, pioneering researchers Margaret Geller and John Huchra embarked on an ambitious survey of galaxy positions, aiming to create a three-dimensional map of the cosmos. Night after night, Geller and Huchra would meticulously measure the redshifts of galaxies, painstakingly determining their distances from Earth. As their map grew to include thousands of galaxies, an astonishing picture emerged. The universe was not a uniform sea of stars, but a vast cosmic web. Galaxies and clusters seemed to be strung like glowing beads along immense filaments of dark matter, punctuated by gaping voids. Computer simulations showed that this majestic web-like structure couldn't form through the gravitational pull of visible matter alone. The unseeable dark matter was key. Like an invisible scaffolding, dark matter's gravity had guided the growth of cosmic structure over billions of years, herding luminous matter into its observed filaments and walls. It was a profound realization. The glittering tapestry of the visible universe was mere embroidery on the dark fabric of the cosmos. Yet even as dark matter's cosmic web came into focus, its fundamental nature remained stubbornly obscure. Faced with a lack of direct detections, some theorists began to wonder if dark matter was the wrong explanation altogether. Alternative ideas bubbled up, proposing modified theories of gravity that could account for the observed effects without invoking any new forms of matter. But for most experts, dark matter remains the best solution to the cosmic puzzle. Its existence is supported by a wide range of astrophysical evidence, from galaxy rotation curves to gravitational lensing to the cosmic microwave background. And while modified gravity theories can explain some observations, they struggle to match dark matter's success on all scales, from individual galaxies to the largest structures in the universe. As we lay back and ponder the night sky above, it's a humbling thought that the vast majority of the matter in the cosmos is essentially invisible to us. In every direction we look, our luminous universe is awash in a sea of dark matter, its true nature still hidden in shadow. Yet the story of dark matter is far from over. With every passing year, researchers across the globe are devising new and ingenious ways to probe the darkness, from ultra-sensitive underground detectors to precision observations of the early universe. The hunt for dark matter continues to push forward the frontiers of human knowledge. It's a quest that has consumed generations of scientists, each building upon the work of those who came before. Perhaps someday a brilliant young researcher will finally unlock the secret of dark matter, unveiling its true identity for all to see. Or perhaps the mystery will endure, forever challenging us to peer deeper into the unknown. But one thing is certain, as long as the spirit of human curiosity burns bright, we will continue to chase the shadows of the cosmos, forever driven to illuminate the dark universe. And so, as we drift off into the realm of dreams, let us hold a space in our minds for the great cosmic mystery that surrounds us. In the darkness lies a glimmer of something vast and profound, a hidden truth that whispers of the immense complexity and beauty of our universe. May we never lose our sense of wonder at the great unknowns that still beckon us from the depths of the cosmos. As we gaze deeper into the sky, we find our universe filled with ethereal galaxies, each one an island of countless stars adrift in an ocean of darkness. But it's the darkness itself that captures the imagination of those who seek to understand the cosmos, because that darkness, that seemingly empty void, is not quite so empty after all. In the early 20th century, astronomers meticulously studying the motions of galaxies began to suspect that something unseen was at work. Fritz Zwicky, a Swiss astronomer with a penchant for bold ideas, was among the first to suggest that some invisible form of matter might be lurking in the depths of space. Night after night, Zwicky would peer through the eyepiece of his telescope at the Palomar Observatory in California, carefully measuring the speeds of galaxies in a distant cluster. As he crunched the numbers, a puzzling picture emerged. The galaxies were moving far too quickly. So quickly, in fact, that the cluster should have long ago torn itself apart, the galaxies flung outward into the lonely dark. And yet there they were, still bound together as if by some invisible glue. Zwicky postulated that there must be some unseen matter providing the gravitational pull to hold these speeding galaxies in check. He called it dark matter, a name that would echo through the decades as one of the greatest mysteries in science. As the years unfurled and telescopes grew ever more powerful, other astronomers would find themselves equally perplexed by the strange motions of stars and galaxies. In the 1970s, Vera Rubin, a brilliant and persistent researcher, provided some of the most convincing evidence yet for the existence of dark matter. Rubin spent countless hours at the Kitt Peak National Observatory in Arizona, patiently gathering data on the rotation of galaxies. Her observations, made with a state-of-the-art spectrograph of her own design, revealed that stars on the outskirts of galaxies were orbiting just as quickly as those closer to the galactic centre. This didn't fit with the visible distribution of mass in the galaxies. The only explanation seemed to be an invisible halo of dark matter encircling each galaxy, providing the extra gravitational pull to whip those outlying stars around at such high speeds. These findings sent ripples through the astronomical community. Suddenly it seemed our universe was dominated not by the shining stars and glowing clouds of gas that we could see, but by some phantom substance that outweighed all the visible matter by a factor of 5 to 1. A new picture of the cosmos began to take shape, one in which luminous galaxies were merely bright baubles afloat in a vast invisible cosmic web. In the 1980s, that web would be given form and structure by the work of Margaret Geller and John Huchra. These two astronomers embarked on an ambitious survey of galaxy distances, aiming to map out the large-scale structure of the universe itself. From the Harvard-Smithsonian Center for Astrophysics, they led a team that worked tirelessly to measure the redshifts of thousands upon thousands of galaxies, using that characteristic shift in light to determine each galaxy's distance from Earth. As their data points began to fill in the map, a stunning vista emerged. Galaxies were not evenly scattered throughout space, but instead seemed to form an intricate lacework of filaments, sheets, and dense clusters, separated by immense voids where galaxies were few and far between. It was a cosmic web of breathtaking scale and complexity, with the invisible threads of dark matter seeming to trace out the scaffolding upon which the visible universe hangs. Computer simulations would later confirm that such a web-like structure could only form and persist if dark matter provided the gravitational framework. In these simulations, astronomers could see the cosmos evolve and unfold, galaxies forming and clustering along invisible filaments, just as Geller and Huchra had observed. It was a triumph of theory and observation, a testament to the power of scientific inquiry to reveal the hidden workings of nature. But even as the evidence for dark matter's existence grew more compelling, its fundamental nature remained elusive. Astronomers could map its distribution and measure its gravitational influence, but they still had no idea what it actually was. The hunt was on to identify the particles that make up this mysterious substance. In laboratories deep underground, shielded from the ceaseless rain of cosmic rays that bombards the Earth's surface, physicists began to construct ever more sensitive detectors, hoping to catch the faint whisper of a dark matter particle interacting with ordinary matter. Scientists like Elena April and Laura Bordis led teams in the painstaking work of designing and refining these experiments, each one a technological marvel of precision and sensitivity. But as the years ticked by, and detector after detector came up empty, some began to wonder if they were chasing a phantom. Alternative theories emerged, seeking to explain the observed gravitational effects without invoking an invisible form of matter. Some proposed modified theories of gravity, suggesting that on the immense scales of galaxies and galaxy clusters, gravity itself might behave differently than Einstein's theory predicts. These ideas sparked lively debates within the scientific community, as researchers grappled with the implications of a universe that refused to conform to their expectations. But even as these alternative theories generated excitement and controversy, most experts continued to favour dark matter as the best explanation for the available evidence, and so the search continues, with each new experiment and each new observation bringing us a step closer to understanding this elusive substance that suffuses our cosmos. We may not yet know what dark matter is, but we can feel its presence in the dance of galaxies and the weave of the cosmic web. It is a reminder that for all our scientific advances, the universe still holds profound mysteries, waiting to be unravelled. As we drift off to sleep, our minds filled with visions of swirling galaxies and invisible matter, we can take comfort in the knowledge that somewhere out there, scientists are peering into the darkness, working tirelessly to shed light on the unknown. And perhaps one day, in our dreams or in our waking hours, the answer will come, and the dark universe will be dark no more. As the Milky Way slowly rotates overhead, we're reminded that our galaxy is just one of trillions in a vast cosmic web that stretches far beyond the limits of our imaginings. And holding that inconceivably immense web together is a substance even more elusive and mysterious than the dark night sky, a material we call dark matter. For decades now, teams of dedicated scientists around the globe have been designing ever more sensitive detectors, deploying them deep underground in specially constructed laboratories, where they sit silently, waiting for the moment when a dark matter particle might finally make its presence known. The researchers tend to these experiments with monk-like patience and meticulousness, shielding their precious instruments from even the faintest hint of background radiation. One of the leaders in this painstaking search is Dr. Elena April, a professor of physics at Columbia University. For over 2 decades, Dr. April has been at the forefront of dark matter detection, developing a series of increasingly sophisticated detectors that use ultra-pure liquid xenon to try to catch the rare interactions between dark matter particles and normal matter. Her work began in the late 1990s with a small prototype detector called Xenon 10, which held just a few kilograms of liquid xenon. But over the years, Dr. April and her collaborators have scaled up their designs, building larger and more sensitive instruments. Today, the flagship of their fleet is Xenon T, a behemoth detector that contains over 8 tons of liquid xenon, making it one of the largest and most sensitive dark matter experiments in operation. Night after night, Xenont sits in its subterranean chamber nearly a mile beneath the Gran Sasso Mountains of central Italy, patiently collecting data as streams of dark matter particles presumably fly through its supercooled liquid xenon heart. The team's hope is that, on vanishingly rare occasions, one of those elusive particles will brush against a xenon atom, producing a telltale flash of light that the detector's array of photomultiplier tubes will pick up. So far, though, despite years of tireless watching and waiting, Xenont and its fellow dark matter detectors around the world have remained silent, detecting no unambiguous signs of the hypothesized particles. But Dr. April and her colleagues remain undeterred. They know that they're racing against time and the odds, trying to catch the first glimpse of a material that has defied detection for nearly a century now, and they're not alone in this quest. Across the Atlantic, at the University of Zurich in Switzerland, another veteran dark matter hunter named Dr. Laura Bordis is hard at work on her own set of experiments. Like Dr. April, Professor Bordis has spent decades designing and deploying increasingly sophisticated dark matter detectors, chasing after an answer to one of the most profound questions in modern physics. Her work began in the early 2000s with the CREST experiment, a pioneering effort to use ultra-pure crystals of calcium tungstate to search for the subtle vibrations that a dark matter particle might produce when colliding with an atomic nucleus. Since then, she's gone on to work on a series of even more ambitious experiments, each one pushing the boundaries of sensitivity and scale. Today, Professor Bordis is one of the lead scientists on the Darwin Project, a massive next-generation liquid xenon detector that will dwarf even Xenon NT in size and sensitivity. Set to begin construction in the coming years, Darwin will hold a staggering 40 tons of liquid xenon, making it by far the largest dark matter experiment ever attempted. But even as Dr. Bordis and her collaborators prepare to break ground on this ambitious new experiment, they're keenly aware of the challenges that lie ahead. They know that they're not just racing against other dark matter hunters around the globe, but against the very laws of physics themselves, because the reality is that, even with an instrument as sophisticated and sensitive as Darwin, detecting a dark matter particle will still be like trying to catch a single grain of sand in a vast desert. The interactions they're searching for are so incredibly rare, and the particles so maddeningly elusive that it could take years, or even decades of patient observation before they finally catch a glimpse of their quarry. And yet, despite the daunting odds, scientists like Elena April and Laura Berdis press on, driven by an unshakable conviction that the answers they seek are out there, waiting to be found. They know that they're not just chasing after an abstract scientific concept, but a fundamental truth about the nature of our universe. Because in the end, understanding dark matter isn't just about solving a cosmic riddle or winning a Nobel Prize. It's about completing our picture of reality, about filling in the vast blank spaces on the map of creation. It's about finally seeing the full tapestry of the cosmos in all its rich and intricate detail. And so, as we lie here in the darkness, gazing up at the faint and distant stars, we can take comfort in knowing that somewhere out there, in deep underground chambers and hushed laboratories, tireless scientists are keeping watch, holding vigil for a sign that the universe's great unseen connector might at last be ready to step out of the shadows and into the light. As you drift off to sleep, lulled by the gentle whispers of the night, know that the story of dark matter is still being written, one patient observation and meticulous experiment at a time. And perhaps one day, when the morning sun rises on a world forever changed by a groundbreaking discovery, you'll awaken to the news that humanity has at last glimpsed the face of the cosmos's most elusive substance. But for now, let the enduring mystery be a lullaby, a reminder that even in a universe as vast and ancient as ours, there are still wonders waiting to be found, truths yet to be revealed. Rest easy, dear listener, knowing that the tireless seekers of hidden knowledge are out there, keeping watch over the secrets of the cosmos, so that we might one day awaken to a clearer view of creation's grand design. And if you've enjoyed drifting off to this gentle exploration of one of the universe's deepest mysteries, consider liking this video and subscribing to the channel for more soothing stories from the frontiers of human discovery. Until next time, may your dreams be filled with the wonders of the unseen, and may the great cosmic mystery forever be your lullaby. Good night.